why it matters for more than just high-end Uber gaming. Because I've seen a lot of news about DirectX12, and it's usually focused on that very high-end, like people trying to sell $600 video cards. But I think we're going to find that DirectX matters for more than just that. So the first question is, how many people are actually interested and might be doing DirectX12 in the next 12 months? A few. How many people might be using things like Metal or Vulkan as a different OS? A few more. Okay. Because a lot of the first half of the talk is really general purpose stuff about why these low-level APIs matter to more than just like high-end gaming. Because they have quite a few impacts for like a lot of different devices. The last bit of it is a little bit more DirectX12 centric. So, yeah, we've got the guy that's on the posters at the side. We're not actually sure who made him at Intel or why he's there, but they put him on front of all the slide decks. So, hey, and it gives me some time to talk again. So, there you go. All right, and as you said, my name's Leigh Davies. I actually work in the UK. I've been working with games developers at Intel for the last 10 years. 10 years before that, I was actually a games developer myself. So the agenda, and I'm going to have to go quite fast. I've pulled slides from GDC, some slides from 2 or 3 different speakers, and I've added a few things of my own into here as well. So the things I want to cover is why DirectX12, why these graphics API overheads matter, what it actually means for power and performance, and then a little bit more specific for Intel, DirectX on our hardware at the moment, something called raster order views, which I gave a talk at GDC about. And there's only a few slides, but I find them really interesting. It solves some really key graphics problems in the computer industry today. And Intel supports it on more than just our new hardware. We've actually been supporting it for the last 2 years. And then some best practices for DirectX12. So the why. Most people talk about this first point. I mean, DirectX12, all the low-level APIs, whether it's Vulkan, whether it's Metal, it's all about trying to improve performance, first and foremost. There are games out there that are CPU bound, and obviously we don't particularly want that. And we also need to improve multi-core scaling. Most of the graphics APIs that are out there today are very much designed around a single-threaded model. And of course, hardware is becoming more and more multi-core. Then, less spoke about is power. That one of the actual goals for things like DirectX12 is to actually improve the performance, the power it actually requires to drive these games. We've got a lot of power-constrained systems out there these days. It wasn't that long ago that if you were playing PC gaming, you would have actually been pretty much guaranteed to be on a high-end desktop system with discrete video card. These days, more and more people are playing on things like Ultrabooks, even tablets. And that means power is a bigger and bigger concern. All of these actually come down to one thing, and it's about reducing the actual overheads of the actual CPU API calls. The actual overheads have always been very undesirable. I think in the 15, 20 years I've been in the industry, people have always been talking about how to check if your games are CPU bound, how to try and make sure they're not CPU bound. And I can remember about 10, 15 years ago, that's just over 10 years ago, seeing NVIDIA on stage saying, like, you know, with the hardware that was available that day, you were limited to effectively 1,000 draw calls. And that was your lot. If you had anything more than that, you were likely to end up being CPU bound. The numbers have gone up, but they haven't gone up massively. But games have become more and more complex. So you still often end up with people that are CPU bound. And of course, most games today don't scale with multiple threads. They usually are profile games with Intel for 10 years. And it's almost always the case, the limiting factor is the time taken to submit the draw calls. So we wanted a way around that. Previously, GPU vendors, especially when they were dealing with like discrete video cards, used to spend a lot of time on their CPU side drivers doing really clever tricks to try and make the graphics look like it was going faster. But it costs CPU time. It does make it look faster from a GPU standpoint, but the problem is today, we're actually in a situation where an awful lot of PCs out there are effectively combining the CPU and the GPU together. And that actually means that even if we're not CPU bound directly in the game, we're actually sharing power between both the CPU and the GPU. And effectively, if you can save power on the CPU, you actually get more to dedicate to the actual GPU. So you'll often find, and one thing I can actually quote, a colleague of mine was working with a games developer, trying to get games running on a 15-watt system, and they found out they could actually get an extra 3 to 4 frames per second, which is a massive thing when you're dealing at something around, when it's running at 25 and you're trying to get to 30. They could get almost the entire game they needed by just turning down the sound quality, which you'd think would be totally irrelevant, but because the sound was all mixed on the CPU, that's effectively was drawing an extra 2 or 3 watts just to the CPU, just for that. They could speed the game up by just changing what they were doing on the CPU. These are some slides I gave at GDC a few years ago when I was talking about why it matters on things like Ultrabooks. Most people, when they go out and buy a PC these days, especially if they're looking at specs, trying to figure out the best thing they can run on, they'll look at the frequencies the CPU runs at. If they've got a built-in GPU in there, they'll be looking at the frequency for the GPU. And you'll see very high quotes. CPUs generally run like 2, 3, even 4 gigahertz. It's great. But today, most of these PCs will actually be sharing the power envelope between both the CPU and the GPU. And what that actually means is that while you can have a maximum CPU frequency and a maximum GPU frequency, it's rarely you get both maximum at the same time, unless you're running at a very high-end desktop system. And when you actually look at benchmarks like 3D Mark, it always looks very much like this graph here. If you have a profile or something like that, you'll see that the CPU workload is really tiny. It probably only issuing like a few hundred draw calls unless it's a test designed to stress the API. And what that means is the GPU gets to run as fast as it possibly can. So the benchmark numbers always look really good. But real games look more like this, where the CPU workload is significantly larger. Obviously games, they've got audio, as I've already mentioned, AI, physics. The graphics themselves are more complex. But what that actually means is all that power needed for the CPU is the GPU can't run as fast as often the benchmarks suggest. And the more aggressive, the lower the power of the system, the more aggressive that trade-off becomes. So it becomes very notable when you get down into 15 watts. And when we start looking at tablets and 2-in-1s that now have TDPs of like 4 watts, it makes a really massive difference how the game has been constructed. And if you're actually burning time on the CPU that's not actually required, it can really start to bring down the actual GPU's performance. So it's very clever. You can see why things like DirectX and Vulkan and Metal all can make a significant difference for these systems that are working in these very low power envelopes. I think we actually look back, and one of the reasons DirectX12 is going down this route of a much simpler API. If you think back to what I mentioned earlier, it was very common for GPU drivers to spend a lot of time on the CPU doing very clever optimizations. It could be doing additional culling on there for the actual geometry as it was submitted. It can be testing which shaders have been set, and sometimes like trying to make changes based on the actual hardware to get best possible path. But the problem is the driver doesn't usually know what application is running, so it's doing effectively attacks on all applications. It's doing tests. So like, we know we can make it go better in this game, and we think this might actually speed it up. So we'll always do this test and make these changes. And of course, if you've got a very well written application, you don't need any of those things. So the driver is effectively like burning power that will speed some things up, but it's going to be an issue for just about everyone, especially as you get onto the low power systems. So a few years ago, Intel actually released a new set of drivers to coincide with the 4th gen core called Haswell, where we took out an awful lot of the actual low-level optimizations for that type of thing, and so it became the responsibility of the developer to write well-behaving applications. We no longer try and do all the redundant state checking behind the scenes. And it went a long way. Well-written applications got a lot faster for us. But DirectX 11 still has a lot of CPU performance on the floor. There are just unavoidable overheads in the API itself. And the point of DirectX 12 is to try and address this. Now, it's interesting to point, like DirectX 12 actually is running on a lot of different hardware today already. Intel actually showed DirectX 12 running at SIGGRAPH last year, so it's nearly 12 months ago now, on current generation hardware. So when we talk about DirectX 12, it's going to be supported by everything from our 4th gen, 5th gen cores, so everything from the last 2 years. So you're looking at like 400-500 million PCs out there that potentially could run DirectX 12 just from Intel. The point of it is it will actually be able to take it another level on. The API is significantly more power efficient even in its current state, and obviously they're still working on the drivers, but we're already seeing very big gains. And what it also means is now everything's been taken out of the driver, and that's as thin as possible. From an application point of view, the things that used to be done by the driver, you can selectively do those optimizations yourself where they make sense. This was a demo that was shown. I'm not going to run it because it would take quite a bit of time again. But you can actually see videos of it on the web, and I believe this is going to get published fairly soon to go with like all the release for like DirectX 12 and Windows 10. It was a stress test effectively. It showed what would happen if you were trying to do like 4,000 or 5,000 draw calls a frame. It was just simple spinning asteroids. It looked quite pretty. And it showed two rather important things. It showed that both, if you were actually running in a totally frame rate unlocked manner, DirectX 12 would give you a much higher frame rate, which is obviously one of the things you want to achieve. But the other thing it showed you was if you actually lock the frame rate at 30 frames per second, then the power consumption for the application running DirectX 12 was significantly lower than running the same application at 30 frames per second under DirectX 11. And the graphs show why. If you're running like totally unconstrained as fast as you possibly could, you could see that the actual CPU overheads meant that 2/3 of the power in the system was actually going just to driving the CPU. Only 1/3 of it was actually being run for the actual GPU power. See the graph on that side, that's going to be less power, same. So that's the 30 frames per second on the left-hand side. 30 frames per second, you can see just how much time was actually spent in the actual CPU. Under DirectX 12, obviously the graphics that are being drawn are the same, so the GPU power stays constant, but the CPU cost effectively about 1/3. On the right-hand side, we've got what would happen if you were originally running on a DirectX 11 at an unlocked frame rate, and then you move over to DirectX 12. Obviously, as the CPU costs come down, the system can now dedicate more power to the GPU, so the frame rate can go up. So you can win-win both ways. You can either end up saving power, running at the same frame rate, or you can just up the actual frame rate. Your choice. And it depends very much on the platform you're running on. So, basically, DirectX 12 on Intel at the moment, we're already seeing very, very significant power savings. And I say we're running on like 500 million PCs already. So there's going to be a large market for all of that. And the benefits are going to be shown not just on the high-end hardware, but also on things like ultrabooks and tablets and 2-in-1s. In fact, I think they might actually be more important for those types of piece of hardware because of the power savings. So that all actually counts for quite a great deal. There's also another thing about DirectX 12, especially for Intel hardware, that's been around for the last few years. And games developers have been asking for a couple of years now. They've been trying to solve things like order-independent transparency, volumetric shadow maps, that type of thing, depth peeling algorithms, K-buffers. A few years ago, Johan Anderson at DICE was saying Intel had introduced a really cool feature with the 4th generation core called Pixel Sync, which actually solved a lot of those issues for him. Problem was, it was only supported by Intel on 4th gen, 5th gen core hardware. And he wanted to see it everywhere. And effectively, DirectX 12 brings that feature set to all hardware. It's called raster order views, effectively, for DirectX 12. The nice thing for raster order views for Intel is it will run on those 500 million PCs. And the other nice thing for anyone developing algorithms and wants to look at this feature, it also means Intel has been writing samples for the last 2 years. You'll see some actually on the, there's some videos playing with a few of the samples that relate to this on the wall. But these things have actually been integrated into games for like 2 years running. So we know that these features that are brand new for DirectX 12 actually run on hardware, even at 15 watts in existing games, and give real visual benefits. And the samples are all out there. And at GDC, I spent some time explaining exactly how you'd port between Pixel Sync and raster order views. And effectively, I reckon it's about 15 minutes work. So, it is really, really trivial. So you can pick up a sample and you can just probably 15 minutes later have it running with DirectX 12. Just to show you what the visuals actually mean when we talk about some of these features, both of these come from Codemasters for various grid titles from the last 2 years. On the left-hand side, we've got something called AVSM. This is what the game looked like originally with the smoke effect when they were donutting the car. AVSM effectively is a volumetric shadow map where you can actually do self-shadowing of the particle system. And you can see what happens when you actually do this. And it's relatively cheap to do. It was really, really difficult with traditional techniques. There are some samples that used to do it, but you would need a $300-400 video card to get it running in real time. We got this running effectively down to 28 watt systems. Would be turned on by default. And you can see the difference it makes. The other one that we had is something called programmable blending. There's samples that show it. But the guys at Codemasters used to have a problem that they didn't use a normal frame buffer. Rather than just being straightforward RGB like normal back buffer, they actually wanted to compress everything down to save bandwidth for their HDR rendering. And everything would work fine. They'd compress everything down, and in their post-process, they'd unpack the actual stuff they'd actually got there and use it for their tone mapping. The problem was when they had transparent objects in the scene. They were effectively they'd already got something in their back buffer that was a compressed data format, and they wanted to blend another pixel on top of that, and they needed to put that in the same compressed format. And that you couldn't just do a normal linear blend between the two. It just basically would not work. And this is what the image would look like normally if you actually cut to the inside carve view inside of Grid 2, Grid Autosport. And you can see the sun up there. And that's not the way it's supposed to look. It should have looked like that. That's what tone mapping should do, where you get the nice blooming effect. And as soon as they actually had the ability to do programmable blending, they could fix that. And again, they turn it on by default on 15 watt systems and above. So there's things out there that you can solve today with raster order views, even on low-end hardware. And just to actually prove the point, AVSM we actually got working on an Android tablet, because very similar extensions are available in OpenGLS 3.1. We actually managed to get that same sample running on 4 watts on a Bay Trail tablet. So if you can run it on something like a 4 watt Bay Trail tablet, imagine what you'll be able to do with DirectX12, where that extension is available to everyone, and you're running on systems going from, obviously from 4 watts again for the Yoga Pro, all the way up to a couple of 100 watts. So the actual, the features that are there in DirectX12 are actually available and can be used on hardware today, and that there's already lots of use cases where you can do some really cool things. And that basically, though, I just want people to walk away from here understanding that there's stuff on the Intel website you can use, and it's ready-made samples for you guys. There's a couple of other things that raster order views do. These are a bit more, some of this is a bit more R&D side of it. They're not actually in working games at the moment, but I've seen samples that do them. Hair is one of those challenging things to actually look right in games. And there's been various samples from different hardware vendors and ways to do it. And most of it does actually involve some form of order-independent transparency to make hair look really nice. Raster order views is a way to actually accelerate that significantly and get nice-looking hair much quicker. It basically comes down to the fact that obviously you need the hair at the bottom nearer the actual skull needs to look significantly darker than the hair at the top. So you need to render that effectively in order to look correct. And it's always tricky as you move the head around. You can't sort all those thousands of like hair strands. Order-independent transparency means you don't need to. There's also R&D in things like decal blending. If you imagine you're writing normal maps into your world for bullet holes onto a wall, they tend to look quite nice when you just splat them into like a normal G buffer. The problem you've got is if the G buffer already has an actual normal map in there that isn't flat. It's like, how do you actually blend a normal map that's just a flat texture over the top of a surface? You can't just do it with normal blending operations. You can sort of fudge it, it'll look okay-ish, but the correct way is to actually do programmable blending again. Then you can read the normal from the existing surface and interpolate the new decal by that amount and write it back in. So it will look technically correct, and it means that the rest of the lighting algorithm for your game can actually pick up on that. And I've seen a few people start to do this now, and as soon as they've got proper decal blending in there, suddenly you find that things that would normally use that data, like screen space ambient occlusion and all those sort of like nice lighting effects, they'll pick up on it. It looks so much better for the decals because they are actually in proper world space, and there's no little artifacts that show up when you try and get close to them. In addition to that, voxels is one of the big deals for ray tracing. You can use raster order views to potentially accelerate the way you build a voxel structure. It does have some trade-offs. That was in the GDC talk, if anyone wants to download it. Because I know NVIDIA spent a load of time accelerating this type of stuff. and what things that they're accelerating don't necessarily reflect directly the way you would use raster order views. But there are trade-offs you can make that, with raster order views, that allow you to insert much more complex data structures inside it when you're actually building your voxel grid. That could actually give you a win in certain circumstances. So there's some very interesting things out there at the moment. Right. So that was just a very brief thing on the raster order views. The last few slides are just general purpose programming stuff for DirectX12. I won't go into them in too much detail. There's not too many people using DirectX12, but some of these are interesting points about what this means in terms of developing games going forward on all the low-level APIs. Probably the most important thing when it comes to all of these, like DirectX12, and I'm assuming Vulkan and Metal's going to be the same. It used to be the case that graphics drivers would spawn their own threads and offload a load of work. And I know a lot of people writing games, if they were running on a 4-core system, they would actually have 3 actual threads in their main game, and they'd always leave 1 free, because they knew the graphics driver would be doing a lot of work. And that used to be one of the best ways to do it. Otherwise, you'd have oversubscription if you had too many threads in your own game, and the driver was off going and trying to do its own stuff as well. These new APIs, they just don't do anything like that. They don't spawn any threads. It's up to you as a user to decide how to use the resources in the PC. So you have to make really good use of multi-threading in all the new APIs if you're going to get the best out of them, because the driver can no longer try and do anything behind your back. The other thing about a lot of these new APIs is they try and, effectively, they've got large state objects that try and put as much context for rendering into a single place as possible. DirectX12 calls it like pipeline state objects, and it incorporates all the blending parameters that you'd normally use. It would incorporate your vertex layouts, your pixel vertex shaders, and it's effectively all gathered into a single data object. And what it means is the driver can actually look at that and pre-compile and optimize that, at creation time. Where before the driver was trying to actually figure out all the different states in the game, and every time you changed one, it would have to try and figure out the best way to configure the hardware. That's where the time was going. DirectX12, it really is a case of trying to figure out the best way to make use of these bundled objects, because you could actually very quickly get state bloat when you're creating a new pipeline state object for just about everything in the game. And I've seen people doing a naive port from a DirectX 11 to a DirectX 12 title, where they've pretty much created one of everything. Every time they make a state change, it's like, I need a new one of these. And that's just going to bloat memory. So you've got to start thinking about it. There's an awful lot of data in here. It's great for context, but you've got to think about the best way to make use of it. Other thing, a lot of these new APIs, they work on the idea of command lists. And the command lists tend to have to be local to each thread. If you were to try and share a command list across multiple threads, you're effectively having to make sure that's all thread safe yourself. So a lot of the samples actually show that you'd end up with 1 command list per thread. Other things to bear in mind is you have things like descriptor heaps, which is you are responsible in a lot of these new APIs for how you manage the memory yourself. When you change, one thing people sometimes do is create a lot of different heaps. The problem is when you actually change the heap, you're effectively flushing the pipeline. So it's trying to actually get as few heaps as possible within that actual scene. So figuring out how to actually organize your memory will make a significant difference. When you actually change the command list, it's effectively free to change the actual descriptors. So it's a case of trying to figure out a descriptor. Yeah. Okay. I think the inheritance one actually comes down to this. The idea of the bundle is it's got an awful lot of state inside the game. If you've actually got state set outside of the bundle, the driver can't know about it, and it causes issues when it comes to the optimization. So it actually recommends you set as much state inside the driver, even if you think you've set it before in the engine, because it allows the driver to actually optimize what is needed for that particular render call. Multi-engine, this is just something I've seen a few game developers doing at the moment, especially when they're using console as their primary dev vehicle. It's true that on the next-gen consoles, a lot of people are actually running compute shaders in parallel to the normal rendering pipeline. That actually doesn't make much difference to Intel. There's no big win to gain there, but I've seen people go into almost pathologically extreme cases to do this, where they've actually tried to pipeline entire things like post-processing as a compute shader, and running that so on the previous frame, so everything's running in parallel. It's like there is no win on Intel for that. That is something that some people do on the consoles to try and get the best utilization of that particular hardware architecture. It's not something that's inherently more efficient than DirectX 12. Last 2 points, just a bit about memory, if anyone does try and start experimenting, because we obviously support DirectX 12 from 4th gen core, which is Haswell and above. Only gotcha on Haswell is there is a limited amount of virtual address space. That's not quite the same as actually like the physical memory. There is, because the way DirectX actually allows like the way it exposes the virtual memory addresses directly to you, so you can actually move stuff around. There is a limited amount that you can actually access. On 5th generation core, the stuff we've just basically released this year, and everything going forward, we fix it. So you effectively can address the entire virtual address space of the PC. There's another one. I'm not sure why it's here, but I know Andrew put this in deliberately for GDC. Try and make sure you're using 64-bit applications if you're doing development for things like DirectX 12. I know a lot of game developers were still shipping 32-bit stuff. If you're moving to DirectX 12 and Windows 10, try and make sure everything is 64-bit. Apparently, you'll thank him later for that advice. And that's basically the summary. DirectX 12, in fact, most of these new APIs, they're great because they're actually giving more control to the end user. Everyone talks about the high performance aspects of them and the fact you can write games with like 4,000 or 5,000 draw calls a frame without being limited by the CPU. That's all true. But there's also a really big use case for going down these new APIs to save power when you've actually got a power constrained system like a 2-in-1, a tablet, or even a lower end laptop. Let's say, the actual point that was made here is I know a few people that did offloading between CPU and GPU. It's a case of think about the most power efficient place to do the actual algorithm. Nothing's free when you've got like a built-in shared system.